start recording so that we don't miss anything. So just a couple updates with respect to your work. So homework 1, I think most people have finished by now, and I have put up your next formative assessment. That is due Monday night. That should not take too long. Remember, the idea is just for you to use whatever you can remember from class as a starting point, and then refresh your memories with your notes as needed to answer those questions. And then I looked at the schedule with respect to what the timing of what we had covered and when your next assignment was going to be due, and I decided that there wasn't enough time yet. So I moved it back a week. So you have a week off with respect to things being due on the 21st, and homework 2 will not be due till the 28th. I figured you'd be very sad about that. Yeah, exactly. I realized this morning that this is my 18th year teaching, and I have not gotten any better at predicting how long things are going to take. I'm still really terrible at it. So what I can say is that I try to pay attention to what's happening and how long things need to take, and if I have to adjust the schedule to reflect that, then so be it. That's my philosophy. So I will never have anything due sooner than I initially put it, but I may push things later if need be. So I did decide to push this one back a little bit. I worked on it today. It's not quite ready yet, but it should be soon, and I'll let you know when that's available. The other thing that I put up on the website was the finished product of the Excel sheet I was typing in last time, and I cleaned it up and finished the columns with respect to the decisions out here. So we had looked at what happens to the significance test associated with our slope as a function of various factors. So for instance, if I have a slope of 6 and it has a standard error of 2, 6 divided by 2 is 3, because the null hypothesis in this story is 0. And if I only have 10 people in my sample and I spent 2 degrees of freedom to be able to estimate the intercept and the slope, then the boundaries for where an area of less than 0.05 would start, given this many people, is known as your t critical value. If I had way more people, the boundaries are moved in a little bit. And someone had asked, what if it was alpha of 0.01 instead? Well, then the boundaries are farther out in both of these. This one is clearly not right. That one went awry. Let me hang on. I had fixed it, and then apparently I unfixed it. There we go. That looks a little more reasonable. The boundaries are further out, but either way, the p-value that you end up with is the same. So these 2 columns here are actually really unnecessary, because they denote where p less than 0.05 starts, but what you get in practice is the exact p-value that corresponds to your t for this many people. So it is harder to get to where unexpected starts if unexpected is only 1% of the time. So the exact p-value, if I had an alpha of 0.01, then this is not significant because it's not less than 0.01, if that's my standard. Neither is this one, or this one. This one is. So it gets harder to say that something is different than expected sampling fluctuation if you set where expected is to be the area for only 1% of the time relative to 5%. So that was what I was hoping to show with this handy-dandy little spreadsheet. So what I did, by the way, if you're fixing it, is just copy this and paste it down here so that it was using these values, but I'll fix it again and repost after class. So any questions on that from last time or today?
I think I have a little question.
You have a little question?
A little bit about alpha. So for choosing between 0.05, 0.03, or whatever, does that take a team of people, or can you start at 0.02 and say, oh well, since it's not significant, I want to make it significant?
Oh, so you're asking for permission to p-hack would be.
Is that what it's called? Okay. So it's down upon.
So where unexpected starts, where your alpha is, or what your alpha is, how often you're willing to be wrong. That's something you're supposed to decide in advance.
Okay.
Now, there are 8,000 different ways to adjust your alpha based on what you're doing to be more conservative. And I'm not going to bother talking about those in this class because they tend not to get used out of a very limited set of circumstances.
Okay.
I would say that if you know, for instance, that you're going to be predicting one outcome and you've got two predictors, right? Alpha of 0.05 is fine for that. But in most research studies, people collect a lot of data. So they might have 10 different outcomes and you might be interested in 5 different predictors. Well, if you look at all combinations of that, that's 50 models. And if you have an alpha of 0.05, that means 1 out of 20 times you're going to be wrong. That means you're going to be wrong like at least twice, like probabilistically. So you might want to be more conservative because you know you're going to be checking a lot of p-values. So if I know I'm going to be running 50 models, I might pick an alpha of 0.01 so that, like, on the whole, I'm much less likely to have flagged something as unexpected that would have just been because of chance.
Okay.
But in theory, yes, you're supposed to pick that ahead of time.
Before.
Mm-hmm.
Okay.
And that's the idea of pre-registration, where you set, like, ahead of time, like in a public place, what you're going to do and what alpha you're going to choose, and then you kind of have to stick to it. There's a whole push to be able to do that nowadays. Okay. We had a question about what is homework versus formative assessments. Homework is doing, using the software to generate numbers and to practice interpret them. Formative assessments are under quizzes and icon, and they are short answer questions. So, like, one of the questions for this one is, give me the definition of a slope. And then I have a little story, like, if the slope is 3, what does that mean? Like, apply that definition to the problem. So the formative assessments are my way of checking in to see if the big concepts are landing, and I read over your answers, and if there's any common misconceptions or if there's things that people want to talk about, then I try to incorporate them into the review that I provide with those questions as a basis the next day. So formative assessments, you get 2 points for doing it at all. It can be completely wrong. As long as you give it a try, you get your points. Homework, you get, each question you get right, you get a fraction of a point, and they all add up across the semester. And just to make sure that it's crystal clear, there are no tests in this class. The grade that you get at the end of the semester is the proportion of points that you've earned out of the total that were possible. And right now it's set to 100 possible. So you know exactly where you stand. All right. Any other questions on anything? No? Okay. Are we ready to look at maybe some software and see how we make the programs actually give us this information? I think yes. I think that's important because in practice, when you actually go to do quantitative methods on your own data, this is what you're going to be doing. And there won't be someone necessarily standing over you telling you if you're doing it correctly. So getting a chance to have some practice at this when you have the chance to be wrong and get feedback should help you in your future endeavors. So I'm with example 2 here. This is going to be the basis of your homework 2. So there is a corresponding set of files on the website. So there is a zip folder that has these files in it. It's syntax and output for each of the 3 programs along with the data that I used to generate it. So when you go to do your homework, I would recommend starting with these files because then you can use them to take the pieces of code, copy them over into your homework file, and modify them as usual, like just as you did in homework 1. But because the code is not at all obvious, like what happens, and because the results are not necessarily obvious as to what they mean, I build these handouts where I have the code in here, describe what it's doing, describe the output, and then I have annotations as to what options mean and how to do stuff. So this handout is meant to summarize the syntax and output across the 3 programs to do this. All right. So the example data are the same data that were featured in the slides. They're from the 2002 General Social Survey. We're going to be predicting annual income in thousands, so that's the example variable, from a linear slope of education, which is what we've covered thus far. And the part we haven't gone to yet is what happens if the predictor to be included in the model is binary instead. So it's a grouping variable of 2 groups. We'll look at those types of models towards the end of this, but we know enough to at least get started. So in addition to learning how to estimate general linear models, I'm also going to show you how to use these additional commands to get extra pieces of information that are implied by the model, but that are not necessarily given directly. So you'll see what I mean when we get there, but I'm making a point that this is going to be something new, even if you've estimated these sorts of models before. I'm guessing you may not have seen these, because this is something that I didn't learn until far too late. And I want to save you from whatever trouble that I had to go through from not knowing this in my past. So there's a little extra pieces in here that should help you down the line. Okay, are we ready to do this? Okay, my Zoomers are like a field of black boxes, and one person put their thumbs up. Thank you, Mo. I appreciate that. Oh, here comes some more virtual thumbs. All right, are we ready to do this, roomers? All the thumbs, excellent. Okay. So first step in all of the programs, bring in the data. This is the part that the starter syntax in the homework assignments I have written for you. So you won't have to redo this part yourself. I have given you code that goes with your homework data. But I want to make sure that this part is included, because that can be the tricky part, particularly when you're using the virtual desktop. Trying to tell it where your folder is non-trivial sometimes. So if you are using SAS, we'll start with that, then this prefix right here, this client slash client thing, that is how the virtual desktop connects to your local machine. So if you just use Windows Explorer and find your folder, that will not work because it's not sufficient enough. This prefix has to be here. And if you use the Windows Explorer in virtual desktop, then it has the prefix. When you copy it, the only switch is that this thing is a $sign instead, and you have to change it to a colon. So I helped several people troubleshoot this step, so I want to make a point of it. This prefix is needed if you're using anything other than the H drive with virtual desktop. So once you have this part, then it is going to fill in this entire path any place that it sees this word. So when it comes down here to Proc Import, this is a command in SAS that allows you to import any kind of data set, Excel, SPSS, Access, what have you. The path to the data set is abbreviated by this file save thing right here, and then the name of the data set with the extension is after. What it is to be called from that point forward in SAS is given by this out right here. So I am calling it example 2, and I am storing it in this work temporary directory so that the original data are safe and sound regardless of what format. And this DBMS stands for database management. It tells it what type. And by the way, most of what I say is already here in a comment. So that way you don't have to write all of this stuff down. But if you look up Proc Import online, you can see the full list of choices for this. For instance, if you're going to import an SPSS data set, they have a .sav type for this, and Access is another one, and so forth. And then the specific sheet I'm importing is right here. Get names means take the first row of data and read it as the variable names instead. And I have a note over here. All SAS commands and comments end in a semicolon. So this right here closes this entire line is one thing. This is another one. This is another one. And then run closes the entire proc import. So everything you do in SAS starts with whatever you're trying to do and ends with a run as a set. Run is like please. Okay, question?
Does the spaces in between proc and import have to be specific, like 2 spaces, 1 space, or does that not matter?
So the question was about spacing. So like if I typed like this, would it work? Yes, it should. SAS is not case or space sensitive except for anything in purple. Anything in this purple that has quotes has to be exactly right. But I tend to write my code in SAS, because the other programs don't let me, such that anything that is a dedicated SAS command I put in capital letters. Anything that you would potentially change is going to be in lowercase or title case like this. And they will turn blue. So you will see the colors when you're working in SAS. And if at any point when you're typing something is red, then something is wrong. Red is wrong in SAS. So if you forget a semicolon, for instance. My husband made a joke to me I hadn't heard before, that SAS actually stands for seriously, a semicolon? Fair. I've once spent like 5 hours tracking down a missing semicolon in a program that wasn't working. So yeah, semicolons are like, if it doesn't work, it's a semicolon, like 90% of the time. Just as a tip.
And you just had to go through and read it all again and just try to find where exactly.
Yep. It didn't work, and it ended up being a missing semicolon that I found like 5 hours later. Yep. So this is why I tell you, like, if something doesn't work after 15 minutes, send me a screenshot. Because if there is a way to screw this up, I guarantee I have done it before multiple times, and we can smell our own. So I'll look at it and be like, oh, yep, that's a semicolon, you're missing it right here. And lo and behold, so let me help. And let the TAs help as well. I should mention there's 3 of them that are either getting class credit or money to help. So don't feel like you're a burden to any of us, because they actually pay me. Did you know that? That I'm not just like a volunteer instructor. They pay me real money to stand here and help you. So don't ever feel bad for asking for help, because that is literally my job. Sure. So this piece. So for right now, I'm not doing anything new to the data other than adding labeling information and making sure that the cases in the data set are complete with respect to the variables that I'm going to be working with. So this is the part that I will write for you in your homework so that you know what the labels are and what the variables mean. This piece right here, when you're working in SAS, is critical if you're going to be working with the data set, because multiple data sets can be active at the same time. Anytime that you want to do something to data, you have to tell it which data set you're doing it to. And this combination of data and set with the same name after both basically means save as itself. So I'm opening this data set on the set statement, adding this stuff to it, and then saving it under the same name. That's what's happening. This last function here is something that you don't need to worry about in homework, but it is something you might need to worry about in life. Because what's going to happen is that anybody who doesn't have complete information is going to get eliminated from your analysis. So to make sure that my sample size stays constant across all of the models I'm looking at, I'm filtering people ahead of time that are going to be missing information. So this if statement, nmiss is a function that stands for number of missing values. So if the number of missing values on these 3 variables that I'm using throughout my example are greater than 0, then kick them out. Now you might say to yourself, Lisa, is that a great idea to just like kick out people? No, but the computer is going to do it anyway if you're missing their information. And you're like, but aren't there better ways of handling missing data? Yes, there are. That's another class. The better ways to address missing data are things like maximum likelihood and multiple imputation, but that's not this semester. I'm happy to point you towards resources if you want to learn more about that, or you can stick with me and we'll talk about it in advanced classes. So all we're doing then, importing data, adding labeling information, and this is the name of the column. This is the label that I'm attaching it, and I repeat the name so that I can see both when I'm looking at the data set. Okay, any questions about the SAS code? Right, Stata code. Stata directly has a way to set a working directory. So that's this cd command. And I was using Stata on my desktop. If I were going to use it on the virtual desktop, I would have to have this piece in front. So I'm actually going to stick that in here. Come on. make sure print is red. There we go. So if I were using on the virtual desktop, that's what it would need to look like. I am using the import Excel command. Case preserve means leave the combinations of capital and smaller letters alone. Just leave it like it is. Otherwise, if you don't have this, it will make everything lowercase. First row means read the first row of data as the variable names. And clear means that if it's already in here, write over it. So you might think, why would I want to do that? Well, if you're going through your program and you accidentally write over a variable or otherwise screw up your data, you can always just rerun this part and get right back to where it was. So this just allows you to start back over if you need to. Label variable then works the same way. We've got the name of the column to be labeled, and then in red here is the title. This is a step that's optional, but it's considered good housekeeping with respect to managing data. And then here's the piece that drops the cases. You don't need to worry about this again for your homework, but I wanted to show you how to do it if you ever need to. So Stata code, relatively briefer than SAS. That's one nice feature of the language. So any questions on this part of the Stata code? Okay. Now R. So can I tell you a quick story about R? This past weekend, I spent, unfortunately, most of it fighting with R to try and get materials ready for my other class, because I'm adding R to that class for the first time, and which means figuring out how to do everything that I know how to do in the other programs. And I was at this part where I was trying to read in a data set and make new variables and make labels, and it wasn't working. But it wasn't giving me any error messages. It just wasn't happening. So I was trying this, and I was like, okay, I'm going to ask for help, right? So I wait till my husband wakes up on Sunday morning, and I'm like, can you come look at my R code and help me? Because he said he'd help me, because he's an R aficionado. So he hasn't had coffee yet, right? So he goes into my office, he looks at my screen, he goes, those are capital letters, and turns around and walks away. And I was like, oh my God, you're right. They were capital letters, and that's why it didn't work, because everything in R is case sensitive. So when you are changing variables and doing stuff in R, you have to make sure you have typed the name of the variable exactly like it looks. And if it's a capital letter, it needs to be a capital letter in your code. And I forgot that, and I was stuck. And I felt very stupid for asking for help, but I probably wouldn't have figured it out otherwise. So R is case sensitive, and so is Stata. So that means that if you refer to this variable like this, it's not going to work. So pay attention to your lowercase and your capital letters if you are working in Stata and R. Learn from my mistakes. So in R, setting the working directory, this can be challenging because of the slashes being backwards. So the slashes are in the opposite direction to what I'm used to looking at in Windows. In R, you can also navigate to where the folder is that you're working from, and then on the window that's on the bottom right corner, there's an option called Set Working Directory. You can do it that way and then copy the path that results. But this is just the same path that I used for all my other examples, just with the slashes backwards, and it ended up working. I am using a function called read Excel, and I am importing the name of the data set here and the name of the sheet in Excel, and I'm creating a new data set with respect to R called example2, capital E, lowercase everything else. And because in R, labels can actually cause problems, I'm not attaching them here. So I just have them as comments in the file that goes with this. And one other piece is that sometimes when you read in different kinds of data, it reads in a format that you can't actually use to analyze. If you need to analyze the data, it needs to be as a data frame. And so this extra piece here just makes sure that it is. So I'm taking the file and converting it into a different type, but leaving it as the same name. Okay, any questions on getting data into R? Yes?
When I try to do the more set as a working directory, I'm having struggles with it coming in on my Mac. On my PC at home, it doesn't have that issue. I was just wondering if you had any ideas of what I'm doing wrong.
You're having trouble with it coming in, you
Yeah,
said?
if I like find it in the folder and then I do like the little gear more set as working directory, just nothing happens.
So if you copy the code that it echoes to the window, or does it not even echo any code?
Yeah, it does that.
Okay, if you steal the code
Uh-huh.
and then put it inside the quotes,
Yep.
does that work?
It stays there, but it doesn't go up into the upper right-hand box as part of the environment, so I can't talk about it anymore.
Okay. I might have to help you.
That's okay.
Yeah, I might have to look at it and,
Yeah, no
and try to
worries.
troubleshoot.
Yeah, perfect.
But yes, and I think all of the TAs have fought with R and won as well, so they should be able to also help with that. Yeah, this can be the trickiest part, but once you get this, you're home free. Okay, so moving on then, unless there's more R questions. So descriptive information. So the same things that you did in homework 1 for practice, introducing you to these systems, I'm going to do here so that we can look at summaries of the variables. So I have in SAS, in Stata, and in R, the same 3 commands, basically. So this is how you would get descriptive information for quantitative variables. So if I'm trying to summarize a quantitative variable, what's relevant? What might I want to know that's a descriptive statistic for a quantitative variable?
It's range.
A range, sure. A minimum and maximum, that would be useful. How about central tendency? Mean, maybe median. How about dispersion? Standard deviation or variance, or both? Yeah. So those are the kinds of things that these routines will give you. Proc means in SAS, summarize in Stata, and a function within the psych package called describe. The variables to be summarized go on the var statement in SAS. They go right after summarize in Stata, and they are inside this C function thingy in R if you want to do more than one. C stands for concatenate. So in R, if you want to tell it to do something to a set of variables, you have to make a list of that set and then tell it to do it to the list. So I am asking for descriptive information for income, education, and marital status. In lowercase, because that's what they are in the data set. The data that I'm working with is example 2. That is specified here in SAS, and it is not specified at all in Stata because Stata has one data set open at a time. So it's like SPSS used to be before it decided to let multiple data sets be open. There is a way to do it in Stata, but it's not as common practice. So when code is not working for you, like if you borrow an example chunk of code like this from my examples and you try to use it in your homework, these are the things that you should check. First thing, am I pointing to the right data set? If you want to use this example on your homework, you'd have to change it from example 2 to like homework 2 or whatever it is. Same thing here in R. Stata doesn't have to worry about that. Next is, what are the variable names that I want summarized? Did I spell them correctly? Because if I left out like Mary with 1 R, it would be like, yeah, I don't know what Mary is, sorry. It doesn't guess. It doesn't try to help you out. Did I spell them correctly, and are they in the right case if you're using Stata or R? And so in your homework, I'll give you a different set of variables to use. You would have to change these names to be consistent with what's in your homework. And in R, the describe command does not give variance, so I added a separate standalone command to get the variance of the variable as well. So the descriptive statistics that each program spit out are in the example files online. So for instance, if I open up example 2 R output, see here, this is what that describe routine gave us. There's the results for that. And then here is the variances for each of the variables. So you can always see what it would look like in the other packages if I don't have it in the handout. But for the models, I've got all that. Okay, any questions on this much? So this is stuff that we already did before, but it's good to see again.
Okay. I was wondering.
Yeah.
I was like, this is what we did in our homework, pretty much.
Mm-hmm.
But
It is.
Okay.
Yeah.
I need to review anyways, but I was just making sure that it wasn't anything different.
No, so the goal of homework was literally just get used to working in SAS data or R and ask it to do something that you already have like a good sense of what that is. Like people know what a mean is. So it's just how do I get that information?
Okay.
I probably shouldn't say this out loud, but you could have done your entire homework using Excel. Because I didn't ask for anything that wasn't just like frequencies or means or things that Excel has. And people used to tell me sheepishly that they did it that way after the fact. And I'm like, okay, but, you know, yeah, this is not new. The new part is interacting with the software to make it give you this stuff. That's what I'm assuming is new. And if that's not new for you, then great.
Oh, yeah, I wouldn't have been able to do it as much.
Question from the Zoomers. When working in R, other than being accustomed with the coding, how do we know what initial functions to run to help the data set work accordingly? Are you talking about importing the data functions or like knowing how to describe things?
It looks like so far you've been giving us what to use to get the thing to set up or to know what to import, right? So like how do you intuitively come up with that? Do you just go to help and try to see what you need to get your data to give you the responses that you want?
So, not exactly. I would say that once you know what routine you need to use, then you can go to the help menu in any of these programs and ask for help using that routine. But if you want to know how do I do this in R, start with the Google. Because you have to know the keywords to search for. And I have also been adding to the website, by the way, software documentation. So for all of the packages that we're going to be using for linear models, I've got the documentation from the program here. So like if you need to learn how to use Proc GLM and what all the options are, you can go here. But if you just don't know where to start, then like how do I do a regression in SAS? And then it will tell you like there's 17 ways to do it, but here's one of them. So I either came across an example or I have code that other people have sent me, because that's how I'm learning R is from other people who are generous with their time. And I'm learning it piece by piece. Okay, did that answer your question? Good? Okay, thumbs up. Okay, so the variables then we're working with in this example, we're predicting annual income. 734 people in the data set. The mean is 17.3, so that means our average person makes $17,300. What does that number tell me? A little bit of review. Standard deviation of 13.8. Yes, sir?
Is distance from the mean?
Yep, average distance of any person from the mean. So it's an index of dispersion for the people in this sample. And right next to it is its friend variance. How are these two numbers related?
Squared.
Which one's squared?
Variance.
Variance. Cough, cough, homework question. So if standard deviation is the average distance from the mean, variance is the squared average distance from the mean. And you might think, well, why do I need to know both? Is because they each show up in a different context. When we talk about how much information in our outcome has been captured by the model, we measure that in a scale of variance. So variance will show up as a model parameter in what we're working with. And then ranges. Always helpful to get the minimum and maximum so that you have a sense of what is possible for your data and whether there might be errors in it. And for this one, marital status is a variable we haven't looked at yet. Note how it's coded. So 1 is unmarried, 2 is married. That means that about 46% of the sample is married. So I would have no idea what to do with this number if I didn't understand the coding scheme, because marital status is not a number. So this is a categorical variable where we have kinds. But as long as it's only two kinds, we can summarize the proportion of the higher coded variable as the mean. All right, so you ready to see your first model? Yay! We're here, right? We may as well. Most of my questions are rhetorical, so. I can manufacture enthusiasm if I need to, right? That's your first model. This is the worst possible model we could ever have, and it's our starting point. This is our friend, the empty model. This is going to be section 1 of your second homework. It has two things in it, beta 0 and E. What is this beta 0? What is the name for that? Fixed intercept, yep, and it is on Y, where the regression line would cross the y-axis, except I don't have a line yet because I don't have any predictors. So in this model, beta 0 is my fixed intercept. If I'm going to predict income, and I don't know anything about a person, what's my best guess for their income? The mean. So that's what beta 0 is going to be. E then is known as the model residual or the model error. And E is how far off the model predicted outcome is from the real one. And rather than focusing on each individual E residual value, what we want to know is how spread out they are across people. In other words, we want to keep track of their variance. So an empty model in software looks like this in SAS. So I've got syntax and output in each of the programs. So the command that we're going to use to do all of our models this semester is proc glm. First thing SAS wants to know, what data set am I analyzing? Example 2. This option right here is something that you can just include in all of your models. It makes it so that it doesn't truncate the names of your output variables. Basically, like in your results, it cuts down the names automatically, and this says don't cut them down unless they're 100 characters or more. So it's just a display feature. Model, right here, is exactly the same as the equation itself. So what y is going to be, it comes first after model, equals, and then any predictors that you would have would go right here. This model does not yet have any predictors, so there's nothing there. And then in SAS, a slash is used to separate what you want to know from additional options about that request. So all of this is options with respect to what is shown in the output, and you can just copy them and use them in your program. The option solution means, can you give me the answers, please? Because that is not a default, crazy enough. Alpha equals 0.05. Can you guess what that might refer to? Yeah, it's going to use that information to provide confidence intervals, actually. It gives us p-values either way, but this is setting up the confidence interval that corresponds to our binary decision as to whether or not a given result is significant. CL-PARM gives us confidence intervals around our fixed effects. So in software, confidence interval is sometimes called confidence limit, and that's why it's CL. So you'll see options of either CI or CL used somewhat interchangeably across programs. And this refers to sums of squares method, not relevant yet. We'll get there eventually. And then to close the request, you actually need two different things. It seems redundant, but it's not. You need a run and a quit, and each of them has a semicolon. It's because you can have multiple models. And so it requires both of these to fully shut it off. And this piece of code and this piece of code go together. So title is adding text to your output. You can have it or not have it. You can write anything you want. But if you don't shut it off, it will keep repeating that text for every single thing that it generates, which defeats the purpose. So having this title by itself basically sets this back to empty so that this doesn't keep printing on every single page. You can type whatever you want in here. I recommend using this so that you have like an eyeball as to what you're looking at in this long file of output. It's like your index as to where the stuff that you want to pay attention to is. Okay. Questions on any of that code so far? Okay, in terms of output then, we got to find our two things. There's a bunch more output than this. I've summarized the parts that are going to be relevant for us for right now. You can ignore every single number in this table for today, except for this one right here. The rest of them we're going to get to in the next unit. But that number right there, it is in a column called mean square, and it's in a row called error, so it's called mean square error. This is my residual variance. Everything else we'll get to because it's not relevant yet. That 190 is exactly the same value that we got from asking for what the variance is of this variable. That is not a coincidence. 190 is all of the variance in income that there is to be had. So the model is telling us that's what's left right now is 190, and that makes sense because there's nothing in the model but the mean. The variance is telling us how far off from the mean we are. So this is simply recreating that in the form of a model. The next thing that we want to pay attention to, also in bold, is right here. That is the estimate of our fixed intercept. In other words, that is beta 0. If we don't know anything else about a person, the best guess for what their outcome is going to be is the mean. 17.3 is indeed the mean of this variable. So that represents our naive starting point for prediction. Every estimate that we get is going to have a standard error that goes with it. Remember what that is? Standard error of 0.51 in this case. What does that tell us? Say it louder. Inconsistency. Yeah, this is about the samples, not about the people. This is the expected deviation of the sample mean from the population mean. How wiggly that intercept would be. If I take 17 and divide by 0.509 here, I get this thing right here, 33, let's call it 34. This is a column for what is going to be our t-test statistic, which is a mouthful, and it says t-value, which is easier to say. And this right here, that thing, is your p-value. The probability of observing a t of absolute value greater than what you found, that's your exact p-value. And this is telling us that p is less than 0.0001. We would see a t that extreme if the null hypothesis were true less than 0.01% of the time. Now, do we care about this number? What do you think? What's our null hypothesis that's being tested by this information right here? Any guesses?
Is it that marriage does not affect the income?
It is, so the guess was, is it about marriage affecting income? In this case, no, because marriage is not in our model yet.
Oh,
This is just income predicted with nothing. So this 17 represents the mean of income. What's the default null hypothesis in software? 0. So this is testing whether the mean of our sample is not 0. So whether people make any money on average. That's what this is testing.
Which is why it's so low.
Which is like, yeah, it's definitely not 0. People make some money. Now, my original question, do we care about this? Not really. So you will get a hypothesis test for every fixed effect in your model, whether you care about it or not. Most of the time, we do not care about a hypothesis test involving the intercept because that's simply testing whether the mean is different than 0. And here's the confidence interval around that. And this out here, by the way, is me being nice. SAS is not going to tell you what your parameters mean. That's me adding annotation to the output. Proc Lisa, as it were. If SAS told people what their parameters meant, I wouldn't have a job. We ready to see the same thing in the other packages? Second verse, same as the first, a little bit louder and a little bit worse. In Stata, the analog to title is display. So this is whatever text you want to write to yourself to print to your output window. The command that we're going to be using to do general linear models is regress. Stands for regression, in fact. Stata code is very untransparent. You just have to know that the thing that comes next is your outcome variable y. The thing that would come after it is any predictors in the model, which we don't have yet, so it's empty. A comma is used to end a command and transfer it to what you want printed. And level 95 here is how you tell it that you want 95% confidence intervals. Note that level 95 in Stata is the same thing as alpha equals 0.05 in SAS. So confidence and alpha are like the opposite of each other. An alpha of 0.05 corresponds to 95% confidence. Here are the two tables that we want to pay attention to. This number right here in Stata is labeled MS, which stands for mean square. Rather than error, they call it residual, but those are synonyms. The 190, that's my residual variance. If I have no predictors in the model, that's all the variance that there is to be had in the outcome. So I've bolded the things that we want to pay attention to. Everything else is not as interesting right now. Now this thing right here, this is our fixed intercept. It is labeled slightly differently in Stata than in SAS. The column for what the estimate is called coef, which stands for coefficient. Those are also synonyms. The other thing is what it is labeled as is underscore CONS, which stands for constant. So people will say this is the constant of the regression equation, like y equals mx plus b, and b is the constant. It is your intercept. After that, the output is the same. So the next column over is your standard error. Estimate divided by standard error is your t. The next thing over is your p-value, the probability of observing a result that extreme or more if the null hypothesis is true. And Stata prints 3 decimal places and then gives up. But this is actually bad. P is never 0. It just means it's 0 to 3 decimal places. So when you write this up, it's p less than 0.001. That's what it is. And by the way, speaking of writing this up, If I go too fast with respect to interpreting these things, or you don't catch what everything is, I want to assure you that you're not actually going to miss anything, because at the end of all of my handouts, there are words. So the last page is going to have an example results section of everything we do, of exactly what I would have written to put this analysis in a manuscript. And this is the type of thing that your homework is going to ask you to do, where there's drop-down menus for the interpretations in each place. So you'll get a chance to practice this, because writing results sections are highly formulaic, so much so that I can train the computer to do it. So at the end of every example, there's going to be text that describes how I would talk about it if it were in a real results section. So just want to put that out there. Remember, the goal is for you to be listening rather than scribbling constantly. That's why I've packed this with information. Little notes here and there are always helpful, but I don't want anyone having to hurt themselves typing or writing. Okay. So we had Stata. Any questions on SAS or Stata so far? Okay, R. More words. Now keep in mind, the green, these are my notes. I'm trying to help you by saying what each of these things is doing. So print is me adding a title. So this is our empty model predicting income. Now, one thing that's different about how R works than the other programs. In the other programs, when you ask for an analysis, it runs it and prints it. It runs it and prints it. In R, you can ask for it to be printed directly, but most of the time you need to ask for further information from that analysis to get everything that you need. And that requires saving the results of the analysis as an object in R. So this structure right here, LM is the name of the routine that we're invoking. It stands for linear models. So you can type help LM in R and you can get a help menu for how to work linear models. And yes, it has to be lowercase or it will yell at you. In linear models, it wants to know two things. What data set am I using? So data equals, and what is the model you want me to estimate? That is under an argument called formula. So what I want to do is basically this part setting that up. So Y is income. So the outcome to be predicted goes here. Zoom in on this. Squiggle, otherwise known as a tilde, I think. Okay, what's my class? It's squiggle. It's the thing that is above the tab key on the left-hand side of your keyboard. That's where squiggle is. This looks like a tilde when I learned Spanish, that was like to make things enye and elye and stuff like that. That's why I call it tilde, but I could be wrong. And one, is that right?
Yeah, it's right.
Okay, thank you. Yeah, I minored in Spanish, but that's like long gone at this point. So I knew I had seen it before. Squiggle. And then a 1. Now you don't have to write the 1, but it is helpful for other things if you do, because there's subsequent output where you have to know the order of the things you've asked for, and having the 1 there reminds you that this is an intercept. So functionally speaking, having a fixed intercept in the model is like adding a variable as a predictor that's just a column of 1s. And if you learn the same stuff using a matrix representation, that's what it would look like. But I'm not going to do that to you just yet. So a 1 stands for the idea that we are asking for a beta 0 intercept to be estimated as part of the model. Okay, so we're just done this part so far. Any questions on just that part? This piece over here then is saving the results of this analysis. And the results have a whole bunch of little sub-variables and sub-parts to it that have the grand total of model empty. So in your R environment, once you run this, you'll see a new thing called model empty pop up over on the right-hand side. And I am doing that so that I can ask it to do extra things besides what happens by default. For instance, by default, it does not print the residual variance like the other programs do. It's like, okay, well, how do I do that? How to get residual variance printed in R. The ANOVA function does that. So I am asking for this saved result to be used in another function that generates predicted variances under sums of squares. We'll get to that later, as well as residual variance. So this is the little table that is created by this ANOVA function. There's my 190. The next thing is I'm asking it to actually print the output that I should have gotten in the first place. So I have these ordered so that they match the other programs. So summary model empty means, hey, can you tell me what happened with that linear model that I asked for a minute ago? And it says, sure. And there's my fixed intercept. There's my 17 that the other programs gave me. It is labeled as estimate. The next column over is standard error, just like the other programs have, same value. Estimate divided by standard error is our t-value, same as the other programs. And I asked it to not use scientific notation. So this is what I get for the actual p-value, which is 0 to many decimal places. And it also prints stars along with this indicating what the stars represent. I have shut that off in subsequent examples because it generates extra output that we don't need. But it appears by default. And then this is me writing beta 0 to help remind you as to what this means. Okay. Questions on that so far? So in the other programs, there's 2 more columns after the p-value, like in Stata, for your 95% confidence interval around that estimate. So I thought, how do I get confidence intervals in R? And the Google sent me to this function, confint. So I'm asking for it to spit out the results of the parameters from this model and level 95, so again, setting the confidence level to be requested. And that gave me this little piece of output right here. So now I have all the pieces of information that the other programs gave me in a few different pieces that it took to get there. And in the example files, so for instance, the output file that I have, you can see it interwoven. So like here's the ANOVA call, and here's that, and then the summary call, and then there's that, and then there's the confidence interval call, and then there's that. So you can see like what each line of code actually generates sort of stuck together like that. I try to pretty it up and label it better than what it does by default. Okay. Questions so far? What time is it? 3:02. Hang it in there. So let's see what happens if we add in a slope. So here's the model that we've been looking at in the slides. So now I want to show you where all those numbers came from. So I'm adding in years of education as a predictor. By the way, if you have a general linear model predicting a quantitative outcome from a single quantitative predictor, this is otherwise known as simple linear regression. That's what this is. So what I am saying is that education should be related to income, but it's not going to be perfectly related. I'm going to be incorrect to some extent. So that's what E's job is here. So E is your residual. The residual always means the same thing in that it's the discrepancy between what the model says your outcome should be and what it actually is. What we are changing is what the model says the outcome should be. Previously, we only had beta 0. So we said, okay, well, I don't know what it should be. Let's call it the mean for everybody. Now we can do a better job. We're creating a linear function here, where beta 0 is the intercept, beta 1 is a slope, and beta 1 is going to tell us the expected change in income for a 1-unit change in education. So this right here is the new, oh, hang on. This is the new part.
So beta 1 is just like saying, like, this is a fixed slope, and then you put in what that is in
Yep. So education it's a column in your data set that you think should be related to your outcome. And beta 1 is like a placeholder for what the model is going to tell you that relationship is going to be. We don't know what it is. It has to be estimated by the data. But it's going to be one number. So note the subscripts here. Income gets an I because everybody has a separate possible value of income. Likewise, everybody has a possible deviation in predicted income. But beta 0 is a constant estimated by the model. Beta 1 is a constant estimated by the model. So I put in education right here in SAS, and otherwise the code is exactly the same. So the structure of the equation is the same as the structure of the model statement. Model y equals x, where you don't have to write anything special to get an intercept. It's automatically given to you. Likewise, oh, no likewise. SAS results first. I'll say likewise, here it is in Stata, where education goes second after the variable to be predicted. And here it is in R, where the new part is right there, plus education. And now I've changed the name of what I've saved this set of results as. So before I called it model empty, now I'm calling it model EDUC for education. So these are names you create. You can name it whatever you want. I try to be consistent in how I name things. They all start with model because that's what I'm referring to. Okay. So the results, then, show you SAS first, then we'll look at the other programs. The two, now we're up to 3 things to pay attention to. Here's this. 162 is our mean square error. That's the residual variance, but now it's residual variance left over. What was it before? Do you remember?
It was just 190.
Yeah, 190 and some change. Right now it's down to 162. So what that means is that the E deviations from how far off each person's predicted outcome is from the one the model says they should have, those deviations are collectively smaller. In other words, we have actually explained part of the variation in income with variation in education. Question?
So if this, it's going down from 190 to 162, if it increased, then we would say that was bad, right? Like we don't want to use that one anymore?
An increase is very rare, but technically possible, and that would mean, yeah, it's like you made it worse.
Okay.
Made what worse?
The amount of variability in your outcome.
Okay.
It can happen if you add a predictor that is really, really non-significant to the point where it's like adding noise and not helping.
Okay.
But it's very rare.
So you would throw that predictor out, or you would just say the whole study's?
I'd throw that predictor out.
Okay.
It's not helping things.
Okay.
Yeah. And we have not talked about this yet, but for those of you who've seen this kind of thing before, Relative to 190, we have reduced our variance. We're left with 163 by about 15%. That's our model R square. That's coming later. So 15% of the reasons why some people make more of the money than others is attributed to education. 85% of the reasons is still here. So this number represents the amount of remaining variation in your outcome that has nothing to do with your predictors. So our two fixed effects, k equals 2 here. Now I've got two lines to interpret. I've got an intercept, which I had from before, and I have education. That number right here, that's my slope. So these column names are not super helpful for telling you what you're looking at. It's like, this is an estimate. An estimate of what? It's an estimate. Of what is the row names here? So 1.82 is the estimate of the slope for education, meaning that's what beta 1 worked out to be in our data. Likewise, negative 7.8 is now what beta 0 worked out to be in our data. It used to be like 17 and now it's down to minus 7. What does it mean? What's an intercept? Say, I'm seeing gestures, but I need words or typing. Zoomers, roomers can do words or typing too. What's an intercept? Close. Where the line crosses 0, meaning where x is 0, right? Mm-hmm. So intercept is always the expected outcome when x is 0. Place of the meaning to start? Yeah, kinda. So like, where does the regression line start? Well, it starts at minus 7. So if I put that in the context of this story, somebody with x of 0, meaning 0 years of education, is predicted to make negative $7,000 a year. Yeah. So that's not wrong, but it's weird. Expected, I'm going to type this in here. Expected income for education equals 0. Weird. What does my slope tell me? How would we interpret that? That's exactly how. We'd say it's the expected income for somebody who's never been to school. I don't have anybody like that in this sample. We're going to fix it next time.
I think the slope means that it's the expected change in income with every 1 year of school.
Yep.
Yay.
Yep. Yay.
Yeah.
Exactly. Yes. Clap it out for yourself. Yay. Yeah, a slope is always the change in y for a 1 unit change in x, or rise over run. In algebra terms, people used to say that. That never helped me, but in case it helps you. Rise over run, whatever the hell that means.
It helped if it was like a fraction.
Yeah, it was
Then
like,
it made sense.
yeah, because then you're like looking at like a triangle kind of thing, and it's like this. Okay. But if you put it in a story, then, okay, what's the change in y for a 1 unit change in x? It's the change in income for a 1 unit change in education, which is an additional year of school. So if I go 1 more year of school, I'm predicted to make $1,800 more than somebody with 1 year less. Is that a lot? I'll take $1,800. That sounds fine to me. Is it noteworthy to write about? We got to keep going down the table. Standard error. How far off from the population slope the sample slope is on average. Expected inconsistency. Estimate divided by standard error gets us to our friend T. T is how many standard errors away from the null hypothesis our result is. How likely is it that we would get a slope of 1.8 if the true population slope were 0? Really super unlikely. Less than 0.01% of the time.
So that means that is probably not $1,800 for every 1 year education.
It means it's probably not 0.
Oh, okay.
Yeah, because 0 is our reference null hypothesis expectation, and we're clear the hell away from that. So we would call this, if the null hypothesis is 0 and we're way, way, way far away from it, that's a reject the null. And in normal people language, that's a significant slope.
So that says education matters.
Education.
When it comes to income.
Yep, education matters significantly. Yeah, the slope is significantly positive. Income is expected to increase significantly as a function of education, however you want to say that.
So when you reject the null, you're just rejecting that it has no significance. That the predictor has no significance.
Yes, you can say it that way. Rejecting the null is saying the predictor has no significance. No significance is the null, basically.
Not enough significance.
Not enough, yeah.
Okay.
And here's a confidence interval for that slope as well. Okay, so next time we will solve this problem of -7. But you already actually learned this. Remember centering?
I was gonna, okay.
Yeah, this is why. We're going to fix it next time. So any questions before we adjourn for the day? Yeah?
I have a question about the syntax. So in the so why we don't have the set syntax?
What was the question? Why we don't have?
So like in the syntax that you saw just before.
Which code? Which program? I'm sorry.
This SAS program.
The SAS program.
Yeah,
Okay.
right. Yeah.
Mhm.
So we have data, right?
Yeah.
But we don't have set SET.
Oh, okay. So the question is, why don't I have a data and a set in here? Because this is specifying the data set as an option to a procedure. I'm not actually doing anything to the data set itself. I'm using the data set as it is to estimate this model. The data set is when I'm going into a data set to manipulate it in some fashion. So data plus set means I'm changing the data set in some way. This just means I'm using it. And the difference is the equal sign. Subtle difference, but yes, good question. All right, we're over time, so I'm going to shut it down, but I'll hang out for a few minutes if anyone wants to ask questions. Otherwise, thank you for coming. I will see you next week. Enjoy your weekends.
Thank you, too, Lisa.
Please do your formative assessments by Monday. Thank you. Thank you. Bye, Zoomers.